All right, so yeah, welcome to the RosettaCV final deliverable.
Right, so basically our kind of goal for this project was to kind of experiment with meta learning and representation learning. We did a lot of we tried a lot of different models and looked at a lot of different papers. It was pretty experimental. So to give an overview of what these are, first of all, representation learning is given a data set, you want to produce a vector of features for each data point such that downstream machine learning problems, i.e. you do stuff with that vector later on, with these features are easier. So yeah, and then meta learning, which is another totally different thing that we were kind of experimenting with, is learning in two loops to minimize expected loss over a variety of tasks. That's kind of vague, but we'll go over later on for both of these, more specifically what we did and kind of what that means. So yeah, the reason why we wanted to do this in general was for data efficiency. So if you have high quality representations, you can decrease the amount of data required. For example, you don't need to account for noise or biases as much. So basically better data means less data needed. And then we can set up our meta learning to learn over task and low data regimes. Basically, with meta learning, we're kind of trying to learn how to learn more efficiently. So if you learn more efficiently, that's another side of not needing as much data to learn well.
Okay, so we wanted to set a baseline. So we just created a CNN, and this is basically, we did something called a few shot data loader. So instead of taking all the images and looking at it all at once, we wanted to take in a very small percentage. So I think we specified this was exactly 1% of data set, and we tested it with ImageNet and potentially OmniGot for the future. And the network structure, so this is basically just a pretty standard convolutional neural network. So there's a couple of layers. The first two are convolutional two-dimensional, going from 1 to 32 layers and 32 to 64 layers. And these are both the activation function for both of these are ReLU, and then also we're doing max pool. So just basically going over the image and getting the maximum of each section that we're going over. And then we have a dropout. So this is pretty random. And a dropout is basically used so that we can, basically it's for random things. When we drop out, will increase the accuracy because it's not going to be kind of prevent against overfitting as well, since we don't want it to be know the training data too well. So we just drop out some features randomly. And then our last two functions are basically just linear. So it's going from 7 by 7 by 64, which is 64 is what we got before. And then 7 by 7 is basically the dimensions of the image, and then that's going to 1,000 layers plus a ReLU, and then finally from 1,000 back to 10, and this is specifically for ImageNet, since ImageNet has 10 classes. And then also for our loss function, it was just cross entropy lost, and this is basically what the structure of the CNN looked like. This is for the MNIST data set, but it's basically the exact same idea, but instead with ImageNet, so just with different images. Our next one was the denoising autoencoder approach. So basically this was our first test as to a framework for representation learning. And we want to provide, kind of like the earlier one, we want to provide a baseline that we will attempt to beat later on with other unsupervised representation learning approaches. So first of all, we trained an encoder and a decoder together, and then we added some extra noise, and then we're trying to learn the identity function. So through this low dimensional bottleneck. So there's an image on the later slide, but basically we have an image, we add some noise, and we try to get back the original image. And hopefully the learned representation in this bottleneck will capture the most important information we need about the image while kind of ignoring the noise. So we don't want to know what the noise is, we just want to get the image, basically add some noise to it and try to get the image back. And the architecture is a convolutional encoder. We have a link for an inspiration later, but it's and a transpose convolutional decoder. So it's just we created an encoder and a decoder to run the images through. And to evaluate, we basically want to train the linear classifier on top of the encoded images and see the results. And by doing that, we discard the decoder. So we're just looking at the encoded images. And then we run the encoder on images from a training task as well as from other tasks. And then in the very beginning, what we did, we have more advanced approaches later on, but we wanted to create a baseline, as I said earlier. So we just checked accuracy after running to convergence as much as possible. And then this kind of set the framework for future approaches to check data efficiency and few-shot learning. And we also want to see how good the dimensionality reduction is. And so we have an image on the next slide that kind of shows what we did. Yeah, so we have an original image, and then what we did was basically added some random noise on top of it. And we wanted to run the image with noise through our encoder and decoder and see if we can create the identity function. So to get back the reconstructed image and trying to learn what's important about the original image while ignoring all this noise.
Yeah, so for our next approach, we use meta learning. Specifically for meta learning, the first thing we tried was MAML, or model agnostic meta learning. The key setup here is that you have a bunch of tasks and you want to learn a model that you can really quickly fine tune to do well on any of the tasks. So sort of you learn what model, or you learn the parameters that are generally do well on all the tasks, and they're able to be fine-tuned to do specifically to that task. Yeah, I guess like I already described. So your problem statement is to try to do well across many different tasks. What is a task? Well, say you have a data set of characters in a bunch of different languages. You could formulate this into a multitask problem where each task is classifying the characters within a specific language. And so we can break up the entire data set into the different languages. And this way we have a bunch of different tasks. And alternatively, what we also try to do is with ImageNet, we just took the 1,000 classes and split them up into bins of 100 classes each and considered that separate tasks. So say, giraffe and elephant would fall randomly into task 1, while learning to distinguish between crocodile and raccoon would randomly fall into task 2. And so our goal here is to try to build a model that is really adaptable to learning how to classify any language we want, or to learn a model that's really adaptable to classify sort of any groups of animals. And so the way this is usually done is in a few-shot learning setup, where you're in order to fine-tune on a specific task, you're only given a very limited number of examples. So you need to have a really good initial model so that you can fine-tune it to a very small data set and still get good results. Like I already said, one of the data sets we used was Omniglot, which is a bunch of characters from different languages. So all you had to do was classify which one was which. What MAML aims to do is find sort of a really good set of initial parameters onto which you can run very few steps of gradient descent, so that you get the best performance on any specific task you can get. So sort of what for any of the different languages, we want to find really good initial parameters such that you're able to only see 2 examples of each letter and run gradient descent on that, and then get really good at telling the letters apart. Yeah, so specifically, I guess if you're interested in the way the algorithm works, is you're actually able to compute a set of sort of fine-tuned parameters for every task. And then you're able to backpropagate that. You're able to backpropagate the loss with respect to the fine-tuned parameters all the way through to the initial parameters and update your initial parameters so that after fine-tuning, you would do even better. Yeah, and you're able to sort of take a look at all the different tasks and see in which direction should you move your initial parameters such that fine-tuning gives you a better result. So some of the problems I guess we encountered with MAML is that it requires a lot of memory because you have to backpropagate through your training step. And sort of that limits, it's very limited through how many training steps you can backpropagate. And so your model becomes sort of very limited. One way to solve this was using Reptile, which is like I guess, which aims to save a lot of the memory and allow you to have a more complex, a longer inner step, but makes some like simplifications and sort of loses the really nice like theoretical backing. All it does is the same thing. You take a look at all the tasks, but instead of actually backpropagating through and seeing what initial parameters would result in a better fine-tuned parameter, all you're doing is you're just moving your initial parameters to the average of all the fine-tuned parameters. So you're basically what you're saying is that like if you want some model that can be really adaptable to learning any language, what you can do is you can train a bunch of different models for every language and then just average all their parameters. And you're saying that like, oh, after we average, if we want to get really good at, say, recognizing like the Latin alphabet, we just need to run a couple gradient steps, and we'll still be able to have really good results for that. So it's not exactly true because some of these like landscapes aren't exactly like well behaved. So if you average all your parameters, you might just get garbage. And if you try to fine tune on that, you might still end up with garbage. But it removes like some of the really have memory dependent steps and allows you to actually train a lot faster. And so in practice, Reptile still works really well, and we saw sort of the accuracy on our training set increase for all the tasks, and sort of loss over all the tasks decrease. So I guess what this means is that the assumption that the average parameters for across all the tasks is a good way to is a good starting point to fine tune is actually pretty true. Yeah, so that concludes the part with meta learning. John, is this your slide?
Okay. So another kind of paper that we implemented was meta pseudo labels. So the goals for this was to apply meta learning and representation learning to improve model accuracy. This is a little bit less related directly to, like, I guess it's like a kind of meta learning thing. It's less directly related to, or like representation learning at all. So we use a semi-supervised approach in order to use unlabeled data as training data. So again, our like overall goal kind of in this project was to make like good models with less data. So in this case, we're trying to use semi-supervised learning, i.e. we don't need as much labeled data. So the approach is to create a teacher model, which learns a target distribution. Basically, it just takes a bunch of like data and tries to label it. And then it passes that to a student model, was trained on the pseudo labels generated by the teacher. And then we used the student's loss on a validation set with known labels to understand the accuracy of the teacher's labels, or to kind of update the teacher. So for our architecture, we use a pre-trained ResNet 34 model on ImageNet, and then the student was a newly initialized ResNet 50. So we prefer the student to be stronger than the teacher, because that's kind of, the student is the final model that we use to run on unlabeled data to try to predict it. So for our training details, during training, the teacher uses some labeled data to update itself. And then we use around an 8-to-1 ratio between unlabeled and labeled data, or this is what it was originally used in the paper. I think in the end, I'm not sure if we implemented that exact ratio. And then for evaluating, once again, we use a student model to evaluate, and we fine-tuned for a little bit in our training, basically just like trained it like a normal model instead of having the teacher basically take the teacher model out of the picture. Okay, next slide. So this is kind of a diagram of how our model, or how the model works. It's kind of like a 4-step process. Basically, first, the teacher produces the distribution as I said earlier. So it predicts the pseudo-label distribution for unlabeled training images. The student updates using those pseudo-labels, so it tries to do a gradient step on that to learn. And then instead of putting more unlabeled images through the student, we put actual labeled data through the student, and that way we know its actual accuracy on the labeled data. And then we use the loss from the student's performance on the labeled data to update the teacher. Right, so yeah, it ends up being kind of like a teacher step, student step kind of thing. It passes off between gradient steps between the two models. Yeah, next slide.
Yeah, so then there's one other part to training here that goes pretty well with meta pseudo labels, and they used it in the original paper, so we implemented it here too. And that's a little bit of an older idea, unsupervised data augmentation. So the idea is we want to sort of regularize the teacher in its training, because if we don't have the teacher learn from the data on its own, what's going to happen is the only signal it's getting for updating is how well the student learns. And that's going to have a lot of variation, because like gradient descent is kind of unpredictable. So there's going to be a lot of sort of variance in our model if we're not careful. So we want our teacher to learn from the data itself. How do we do this? One part of it is supervised loss, which is just ordinary image classification. So we take some batch of labeled data and we say the teacher should try to match the labels as best as possible. So if you see the diagram on the bottom left-hand side here, that's the supervised cross-entropy loss. The other side is this unsupervised consistency loss. And this is a sort of contrastive approach, which is really common in unsupervised learning. So the idea is we're going to randomly augment some unlabeled images we don't have labels for. And what we mean by augment is we're going to do some crops. Maybe we'll block some areas out, shift the color a little. So stuff that doesn't change what it's an image of, but it's going to look really different to our model. So like, for example, if we reflect it, our model's going to see that completely differently because it's just a bunch of numbers. But to us as like humans, it's still the same semantic thing. So we want our teacher model to output the same sort of thing for differently augmented images, right? If we reflect it, it should still be a cow, for example, right? Okay, so that's really common in unsupervised learning when we have no labels at all. But when we combine it with this supervised cross-entropy loss, the representation that we learn is encouraged to be the labels of the image itself. So this is a semi-supervised method, which says like, we're gonna have some labeled data and we're gonna weight that loss so it's encouraged to learn the labels. And then we're gonna have a ton of unlabeled data and we're just gonna make sure that it predicts relatively consistent outputs there. So a couple connections to what we've talked about so far. It's a little similar to denoising autoencoders, only instead of that random noise we saw before, now we have like bigger noise, like flips and crops and rotations. It's a little bit like MPL on its own, because in fact, one way you can view it is when we're enforcing this consistency loss, that it's like we're training a pseudo label, we're training it to generate its own pseudo labels and to match those for different noise. So it's a little similar to stuff we've talked about so far, but again, it's this natural extension to MPL that lets the teacher learn from all the data as well. And yeah, that's UDA. Next slide, I guess. So results. The results from the original authors are very good. It's state of the art on ImageNet. So 90% top one accuracy is like really, really good on ImageNet. Our MPL implementation, unfortunately, we don't have quite as much compute resource, which we'll talk about in a little bit, but we got about 65% accuracy on the test set with just 100 epochs, which isn't too much. And that's 60% of the data. We used CFAR10 because it's a smaller data set than ImageNet. ImageNet would take forever to load with our compute resources, but this sort of is promising that we were able to replicate the general idea of the paper and get good results with less than the full data set. So also we're looking into this sort of JPL Mars rover imaging as a potential application for this, because we have a data set where there aren't too many labeled positive examples. So it's like it's mentioned there, we have a ton of unlabeled data that maybe our model could learn from, and only like 5,000 labeled, 1.5 million unlabeled. So there's a bunch of issues in terms of like loading the data when you have that much there, normalization, pre-processing. So we tried training with MPL without fine tuning, and it didn't give us great results. It was a little bit closer to a random agent. So that just means we would need to modify the hyperparameters a bit, maybe weight the losses, and we'll talk about sort of future approaches about how we could fix these sorts of problems in a couple slides, I think. But that's meta pseudo labels. It fits into the overall arc of our project in that it's learning to learn with less data, learning to learn more efficiently, sort of in the same way as MAML. And actually part of the math behind meta pseudo labels is based on MAML. So all these ideas interconnect. It's a really new field and it's exciting to see where it's going to go next. On, I think, to contrastive multi-view coding. Yeah.
Yeah, so I think this is my slide, correct me if I'm wrong. So the main idea between contrastive and multi-view coding is that, we want to have the same representation of data under different sort of views of, that same image. So I'm just gonna click through a lot of these slides and just go through. Yeah, so generally, like, what do we mean by when we say views? Well, views can be like different ways to look at sort of the same data. For example, it could be in this like small image, I don't know if you can see, but there's a picture of a classroom. One view could be sort of just taking the RNG channels of an image and maybe just killing the blue channel and, calling that one view. Another view could be the grayscale. One view could be sort of the depth perception map of an image. And one view can actually be just the caption of an image itself. And so what we want to build is sort of an encoder for each view that will eliminate the view from the representation and only have the sort of semantic content of an image. So like a banana, when grayscaled, when like, inverted, when you write the word out banana, between all these encoders for every single view, we should still have the same representation. And what that tries to achieve is it tries to make sure that the all the encoders are sort of robust against noise and against things that don't actually encode the semantic contents of the image. Yeah, and the way you're able to actually learn this is by having something called a contrastive, just with contrastive learning, which all it does is has two encoders, or has an encoder for every view. And you take pairs of images that are, the same image, but just from different views. You encode them and make sure that the encoding space is as close together as possible. And you might say, well, what if all of the encoders just predicted all zeros? So every image would technically be as close as possible together. Well, that's where sort of another trick comes in, where you're not only pushing together images that are the same images from different views. You also need to be pushing apart images different images from different views, and like different images from the same view. So a banana, as an example, a banana grayscaled and inverted, you're trying to push together, while a strawberry grayscale and the banana inverted, you're trying to push apart, so that their representations are different. And sort of what we try to do is we try to extend the idea of these matching views as much as we could. So what CLIP, which is like a pretty recent OpenAI paper, has shown is that there's a lot of really good representations you can learn if you take a caption as one of the views, and the actual image as another. Just because on the internet, you have so many of these, you have so many captioned images that you're actually able to, you're able to utilize all this massive data really well. And they show that empirically, like this idea of contrastive learning does really well on these like large data, labeled data sets. Well, what our idea is trying to add a translation loss. So rather than just having a encoder for every view, we also had a decoder for every view, and we learned a mapping from view 1 into the latent space, and then a decoder into view 2, and add another loss that sort of try to train a decoder for every single view. Oh yeah. Another thing we did is sort of domain confusion, which is the idea that latent embeddings should only hold information sort of on their subject. So it involves training another model that tries to predict what view. Yo, dude, that was pretty epic. I was in the middle of presenting, and like I think our recording broke too.
Wait,
oh, Oleksii.
Yeah.
Damn, dude, someone moved me to a different room. That's tough.
Oh, what the hell?
Yeah, I think they were trying to troll, but they didn't realize I was presenting. Yeah, so CMC++, like I was saying, domain confusion. You have a model that tries to predict what view you are embedding from, and the main goal of the encoder is to try to have an encoding that's agnostic to the view that it came from. So if you're it's sort of the idea of like a GAN, where you have a discriminator and a generator, except this time it's an encoder that tries to confuse the discriminator. And we also threw in a bunch more views. So we had like things like saturation, image saturation, image inversion, grayscale. Yeah, we basically combined like threw together ideas from CLIP, ideas from other I guess adversarial models, and I wanted to see if we put all of these losses together, what would happen. So we found that like a lot of our losses that we wanted to converge didn't actually end up converging. So when we trained, so sort of our results, or when we trained on 1% of the ImageNet data, our training accuracy on the CMC features was 9.81%. For context, if you had a random feature extractor from a random feature extractor, that just mapped an image into some random latent space, you would get 0.06%. And if you actually trained on raw pixels, you would have only 0.8%. So what we showed is that if we put a linear classifier on top of our CMC features, we get much better results than training on the pixels itself. So even though we had like 1% of the data set, we are able to build a sort of representation, for images that allowed a linear classifier to actually be really good at predicting what class the image is. However, our results weren't very competitive with the state of the art, mostly because a lot of the losses that we experimented with didn't end up converging. And so we think that a lot of this came from there being a really large variance in the gradients, and training all of these losses, sort of alternating between training all of these losses, sort of stopped all of them from converging at the same time. So what we did learn is that oh, actually, is this my slide? I feel like I'm not. I feel like I shouldn't be doing this slide.
I can do this slide.
Okay.
Yeah. So this is mostly an educational project. So a few things we learned are, one, machine learning is hard. So even state-of-the-art models do have straightforward foundations, right? So just push the images together, but really implementing them is trickier. They're really dependent a lot on hyperparameter selection. So they're still a bit brittle. That's just the risk of going with state-of-the-art models here. Also, the field moves really fast. So this is one of the most heavily researched things in visual machine learning. So metapseudo labels was actually just released March 23rd. So we're yeah, this is great, state of the art. So we implemented it. And then Facebook just came out with Pause, which was released about a week ago. And if you look in the bottom right-hand side, you can see up left is better. So up is more accurate, left is less training time. MPL is that little triangle in the middle. So we thought that was great because it was an outlier. But in fact, now Pause was released and you see takes fewer epochs, does even better. So more room for trying that out in the future. Interestingly, actually, Pause uses a sort of student-teacher architecture similar to metapseudo labels, but that's a different story, I guess. Big limitations were compute and memory. So with these types of projects, we're using CSUA servers. That's not what Google DeepMind has on hand. And these tasks are really resource heavy. So like Oleksii was saying, we have to sort of, in some of them, we're almost back propagating. We have this inner loop, which is like a task, especially in meta learning, which means one whole supervised learning thing is on the inner loop. Just put that whole thing in a for loop. So now, it takes a lot of resources that we don't necessarily have. So we have to evaluate it not just in a low data regime, but a low compute regime. So in terms of future work, how can we deal with these limitations or advance things? One would be sort of more explicit combination of meta learning with representation learning. So we didn't as much get the chance to sort of build on top of our representations or these semi-supervised methods for something like Reptile plus MPL, let's say something like that. So Dino, which is also released by FAIR with Pause, explored sort of centering and sharpening the teacher network. That was one of their things. So we could just throw that on top of metapseudo labels. Also getting more experiments, as mentioned before, with MPL or another feature extractor on the JPL dataset, because we think that's a cool task to solve. Dataset GAN, which is one of my favorite papers, we could look into that, which says, let's not do student teacher, let's actually have a GAN create a bunch more labeled data for us. And actually that works really well, strangely. And then also for CMC, all these sorts of things, this hyperparameter search, training it for longer, mostly again, because of compute limitations, but there's a lot of good first steps that we think we did. And it's sort of now gated by the amount of GPUs that we have on hand. Yeah, so that's most of this project and the learning that we had along the way. I had a really good time. There's other approaches we were looking into, like contrastive losses, but I think we're going a bit over time here, so I'm happy to leave it at that.
Yeah, totally. Any questions? I think we covered like a lot of content. So if you're interested in anything, feel free to ask.
Yeah, I was a bit confused about how exactly you trained like the teacher model.
Yeah, that's a really good question. So the teacher model, you can train it from scratch. In general, we start with, in this case, a trained ResNet on a supervised task. So we have weights that are already like pretty good, but the teacher model is trained in two ways. So one way is with that UDA loss that we were talking about. So be really consistent on the unsupervised, on the unlabeled data, and on a little bit of the labeled data, make sure it's doing a decent job. The other thing that's the beauty of meta pseudo labels is the teacher is trained to improve the student's performance the best. So that's the teacher's main objective, is not actually to classify the data correctly, but to classify the data in such a way that the student learns the best. So say, for example, we have like a really ambiguous picture. If we were trying to solve the supervised learning problem, then the teacher would try to confidently make a guess and be like, that's a cat. But in the meta pseudo labels, what it might instead realize is the best way to teach the student is to be unconfident, to say like, we don't really know what this picture is. So it's a little bit different than just trying to classify the images. Instead, it's explicitly trying to teach the student as best as possible. And the math is a little tricky, but it's in the paper.
That was pretty helpful. Thank you so much.